Okay, let's move on. Okay, so the next talk will be on the usefulness of linear modular arithmetic in constraint programming. And I think that Gilles will be giving the presentation. Can someone please roll the video?
Hi, my name is Gilles Pesant from Polytechnique Montréal, and I'm here to tell you about our work on linear modular arithmetic constraints in constraint programming. Work that was carried out together with my former master's student Mahshid and Kuldeep Meel at the National University of Singapore. So first I'll define what we mean by such constraints and tell you why we should bother with them. Then we'll move on to filtering algorithms for them, look at an application to model counting, and then wrap up and tell you where we want to go next. So we are interested in constraints of the following form. We have a vector of n integer finite domain variables x. We're looking at linear combinations of those variables. So there's a vector A of integer coefficients, and that linear combination can be upper or lower bounded. And I'll take in modulo P. In particular, we'll be interested in systems of equality constraints in modular arithmetic, so a system of m equalities in n finite domain variables. So why should we care about such constraints? Well, they appear naturally in several applications, cryptanalysis, for checksums, hash functions, which we'll use in the model counting application. So they could be useful to model problems in CP. And so we believe that they deserve more visibility in the community. They're not in a global constraint catalog, despite the fact that they were introduced almost 15 years ago. We'll see in a moment. I don't think they're supported by solvers, despite not needing much of anything new to implement them, as we shall see. So let's look at those filtering algorithms. As I said before, they've been introduced, those constraints have been introduced before and in the context of model counting. And these authors basically considered the same algorithms as we consider here, but with some important differences, and importantly reached different recommendations about their use, as we shall see. So looking first at individual constraints, linear constraints. Now, if we weren't in modular arithmetic, we would typically enforce bounds consistency. It's cheap and can be fairly effective. Here is not as trivial to enforce and would likely not be effective at all, as we will see in a moment. Another algorithm that was introduced by Mike Trick in 2003 and that achieves domain consistency is based on dynamic programming and builds a layered directed graph that is a compact representation of the set of solutions. So we see such a graph here. We've seen it something similar for the regular constraint later on, and MDDs are also closely related. We can use the same algorithm here. Let me first recall that approach for standard linear constraints. For example, 2x1 plus 4x2 plus x3 plus 3x4 equals 4. Domains the same for every variable, 0, 1, 2, 3, 4. You would build the graph illustrated here. There's one layer per variable. The arcs in the layer above a variable represent values that are assigned to that variable and participate in the solution. And you would, for example, for x3, see that there is no arc labeled 3, which means that value 3 can be safely removed from the domain of x3 because it doesn't belong to any solution. Fine. What happens in modular arithmetic? Well, for that same constraint, but let's take it modulo 5, your state space graph now looks like this. Much more dense. There's nothing we can filter, everything's supported. And that's typical here, that your graph will be much more dense. It may get a bit easier if the domains have holes or not, but still, In practice, as was remarked by Gomez et al., and we experienced the same thing, observed the same thing, you only want to apply it when the number of unbound variables is fairly small. Otherwise, you're working hard for nothing. Okay? So that's a bit of a bad news. Now for some good news. If we look in particular at systems of equality, so AX equal B, but taken modulo P, there's an old algorithm, Gauss-Jordan elimination, and probably much older in the 19th century actually, that works very well over the real numbers or rationals, but we cannot use usually on our finite domains, except that if you take them modulo P, P being prime, they define a field and basically the algorithm works. So that's the good news. So as a first step, we can apply good old Gauss-Jordan elimination to simplify our system of equalities and reach our parametric form, where basically you split the variables into the parametric variables and the non-parametric or dependent variables. So it gives you a more structured representation of the solutions. And as we usually can by that process of Gauss-Jordan elimination, we may detect unsatisfiability of the system. So that's the first step. That's something that was considered by Gomez et al. As well, but they said, well, it'd be too inefficient, and they just abandoned it. So one first important difference here from that work is that we go further and we take advantage of, I guess, a bit of progress since their work. So our second step, we basically rewrite that system as a table constraint. So once you've got the parametric form, you iterate over the domains of the parametric variables. Now, if you evaluate the expression on the right-hand side, it gives you a value for the left-hand side, but those dependent variables are not truly free variables, right? They have their domain. So you still need to check that each equation is satisfiable, that the value of the right-hand side appears in the domain of the dependent variable on the left-hand side. And you collect these solutions, so consider them as a set of tuples, and then you maintain domain consistency on that using here, in our case, a compact table implementation. So an efficient way to do this. And that makes a big difference. So in practice, though, you don't want to post a table constraint unless the number of tuples is not too large. You can imagine that it can grow quite large. So we determined experimentally that under 1,000 tuples was a good compromise to not to have too heavy a set of tuples to maintain, data structures to maintain, and getting some interesting filtering. And in practice, what we actually do, we don't post and then retrack upon backtracking all those table constraints. We actually use the algorithm for compact table directly in the constraint. So that's a bit lighter, and in practice makes a bit of a difference. So that's a main difference here from the previous work. And actually, in our experiments, we come to the opposite conclusion from Gomez et al. Whereas they used small linear constraints in modular arithmetic and only applied the dynamic programming algorithm. We found that actually it's better for equality, in the case of equality certainly, to just use the Gauss-Jordan elimination algorithm and not use the dynamic programming one for individual constraints. And overall, that gives you a better performance. So now let's see how we can use our constraints in an application to model counting. So what's model counting? So you're given a CSP and you want to compute the number of models or solutions to that CSP. So that's a hard problem. It's a sharp P complete problem. Think of it as the equivalent of NP hard, but for counting problems. Yet there are important applications, notably in probabilistic reasoning, so you still want to solve such problems. Exact approaches have been developed, as well as approximate ones. Among the approximate model counters, there's the approach based on hashing that's quite interesting for its theoretical guarantees. So it uses hash functions because of their property of mapping elements evenly in the image space. And further, you'll want pairwise independence of hash functions, so that successive applications of hash functions preserves that guarantee. So the idea is that we use several hash functions, pairwise independent, and that will partition the solution space of your CSP into roughly equal small cells of solutions. So if you use m hash functions, each mapping to p-values, you'll create p to the power m cells. And at some point you stop and you enumerate the solution in a single small cell and then extrapolate the result. So that's the idea behind this. Now, it was initially proposed for SAT, so model counting for SAT models. There it uses random XOR or parity constraints as hash functions. For CSPs, you can generalize and use random linear equalities modulo p, where p is prime and at least as large as the domain size. So here is where our constraints come in. So here's an illustration of the idea. So every dot here represents a solution to your CSP. So you pick a linear modular constraint uniformly at random. So here AX congruent to 2 modulo 5. The coefficients A are chosen uniformly at random. The right-hand side 2 as well. And so it divides fairly evenly the set of solutions into 5 slices here. And say with that constraint, we would take the third slice right in the middle there. Those are the red dots. And then you, by adding this constraint, you just focus on these red dots. Those red dots, so you can further apply, so with another hash function. So A prime X congruent to 0 modulo 5. So you slice into 5 again, and here you're left with the green solutions. And so eventually you stop. Maybe you stop here and you enumerate, you count these solutions, the green dots, and then extrapolate the result. Here you would multiply it by 25, 5 to the power 2. Okay, so we run some experiments, first on synthetic instances. So we define a problem. We've got n variables, domain, the digits 0 to 9. 2 constraints that don't overlap. An exactly constraint on the first half of the variables, saying that value 0 should appear 1/3 of the time in that half. And an all different constraint on the second half of those variables. Now, because of the very clean nature of this CSP, we can actually compute the number of solutions analytically, exactly. So we have something to measure up against. We used p equal 11, so prime and above greater than 9. And in these results and all the ones that will follow, each table entry is an average of 30 runs. So here are some results for instances of size 10, 15, and 20 variables. So we want to see, as we increase the number of constraints that we add, what the impact is on runtime and on the accuracy of our counts. So for n equal 10, though in the second column we see that we've got the actual number of solutions, we enumerated them. It took 5 hours. If you compare to adding 5 constraints here, you see that you get under a second an approximation that's under 1%. So very good. And the same for the other two. We didn't dare enumerate solutions. It would take weeks. But you see that within seconds or minutes, you get an approximation that is under 1%. Now, do we need to do something as complicated? Maybe we can just, for the same approach of focusing on a small cell, we just pick m variables at random and pick values in their domain at random as well. That would be simpler, certainly. But as the last column indicates, the accuracy is very bad. You see that it's much larger. It doesn't get better either. So never gets to within 1%, far from it. So it's really important to have those constraints with their theoretical guarantees. Next, we looked at 3 sets of benchmark problems from Gomez et al. First one, n queens. The search space is not as densely populated by solution as the synthetic instance, so the improvement, the speed up is not as spectacular because you cannot add as many linear modular constraints before getting to a cell that's has too few solutions. Still, we get some very close approximations. If you want to compare to Gomez et al., their approach is a bit different. So they use short constraints on 6 variables at most. So you don't get the same guarantees. They don't count in a cell. They repeatedly test satisfiability in a cell without going into details. And that yields a lower bound. So for example, the 15 queens, their lower bound is about a factor 6 too small. Next, spatially balanced Latin square. So that's a more constrained Latin square. Very few solutions actually. And so here again you see, so we computed the exact number of solutions and we see that we cannot, once we add 1, 2, maybe 3 constraints, the number of solutions in the cell is too small and we lose accuracy. So we there's a moderate speed up. We get an error that's within 1 or 2%, maybe in many cases. And to put things in perspective, Gomez et al. For the size 14, order 14, order 15 instances have lower bounds that are factor 47 or up to 2 orders of magnitudes too small. Finally, some graph coloring instances. Lots of solutions here. You see that we can add quite a few modular arithmetic constraints. Very close approximations. For the second instance, we did not dare compute, enumerate all the solutions. That would take a very long time, but we see from the convergence of our results that we're likely to be quite close. And within half an hour, we get a quite close approximation. For comparison, Gomez et al. On that instance, have a lower bound that's factor 30 too small. So to wrap up, so our takeaway message is that supporting linear modular arithmetic constraints in CP is useful. You saw an application model counting. In the paper, there's an illustration on checksums as well. And that you don't require that much extra work in terms of implementation because we're reusing a lot of the known algorithms. What do we want to do next? Well, we'd like to, one limiting factor is the number of tuples that we can use in our table constraints before, so it stays efficient. We'd like to have earlier filtering on larger tables, so maybe using smart tables for that. Using inequalities for model counting, and we prove a result in the paper. That's for the case where the number of solutions is not very large and goes down too quickly, so you can't add too many constraints before you're left with just too few solutions in a cell. Using inequalities should solve that problem. And eventually we'd like to build an approximate model counter for CP. That's all. Thank you.
Okay, questions? Peter.
So one thing the SAT model counters do is rely on Gaussian elimination in the no-good learning, like to reduce the amount of work they have to do. Is there any chance we can do the same for these linear equations?
Maybe I'll let Kuldeep may have a bit better insight than me on this. I think he's there. Yes.
Yes. Yeah. Sorry about that. Yeah. I mean, in principle, yes, we can do the similar propagation of what we do in crypto-set, where the constraints that you learn from the Gaussian elimination are propagated back to the CNF part. It would be certainly interesting to see it.
Thank you.
I have a question. So approximacy guarantees, are they holding here?
Yes. Well, we did
Because
not
there
implement
wasn't
a
a
fully.
mention.
Yeah, we did not implement a full model counter because we wanted to just illustrate a prototype of working. But if you use a hash function, these linear modular constraints that we are using and put it in the entire approximacy framework, then you do get the current formal guarantees.
Okay, and then the other part I didn't understand was the mention of the previous work, Gomez et al. Being where Gilles was saying that they said that solving the equations was inefficient. So I didn't understand why is it inefficient, because Gauss-Jordan is not inefficient.
Well, they mentioned that they did not implement it. They decided that it would be. I mean, they decided without implementing it. They just judged that it would not be that the dynamic programming would be a better path to follow.
Okay, so they just chose a different path, but not as you show in yours, right? It's not inefficient, right? And it shouldn't be inefficient, I think.
No, but I think having a good way of handling all those solution tuples, having an efficient table constraint, I think makes a difference here.
I mean, you look at the simplex solver, right? It's doing equation solving. I mean, not this type, but it's not different. Pivot is just equation solving, right? And that's doing, gazillions of equation solving on very large equations, in fact. Any other questions? Anything from the Vienna side? I can't see. No more questions. Okay, maybe we move on to the next talk.